Good morning, all. Today I am going to discuss a very important topic in unit number 3, which is nothing but instrumentation amplifier. Instrumentation amplifier. Today I am going to discuss about this topic, instrumentation amplifier. Before going to discuss about analysis of instrumentation amplifier, we have to define what is instrumentation amplifier and what are the good requirements of instrumentation amplifier. And then next I am going to discuss about analysis of instrumentation amplifier. First, in this class I am going to discuss about introduction of instrumentation amplifier. Okay, introduction of instrumentation amplifier. And second, I am going to discuss about good requirements of instrumentation amplifier. Good requirements of instrumentation amplifier. Last but not the least, third one is analysis. Okay, analysis of instrumentation amplifier. And fourth one I am going to discuss about advantages of instrumentation amplifier. Okay, in this class I am going to discuss about all these things. So first I am going to discuss about introduction of instrumentation amplifier. Many industrial systems and consumer systems, process control systems requires precise measurement of physical quantities. For an example, if you consider a sugar factory, there we require precise measurement of flow, level and temperature of juice. And coming to the second example, if you are considering the plastic furnace, there we require measurement of temperature. And if you are considering the dairy plant, there you are going to precise measurement of humidity and temperature. And these physical measurements are required for good production of the output for the industries. That's why we are going to measure the physical quantities. And generally the outputs of the physical quantities are generated from the transducer. Now here we have to know about what is a transducer. Transducer is nothing but which converts one form of energy into another form. For an example, if I am considering the thermocouple which converts temperature into electrical signal, whereas microphone converts sound energy into electrical signal, strain gauge converts pressure into electrical signal, and this output of electrical signal is mainly used to operate other parts of the system, or it is used to display the physical measurements. And coming to the main usage of the instrumentation amplifier. What is the main usage of the instrumentation amplifier is we are going to amplify low level signals by using this instrumentation amplifier. It is not possible in case of differential amplifier. It is only possible in case of instrumentation amplifier. That's why instrumentation amplifier is mainly used to amplify the low level signals. And next, what I am going to tell you is generally the output of the transducers are low level signals. So to amplify that low level signals, we require the instrumentation amplifier. And also practically the transducers are placed or mounted on the top of the equipment and control from the and remote from the control location. So whenever you want to get the output from the transducer, we require long wires or cables or transmission lines from the equipment to the control room. So while the output signal of the transducer is coming from the equipment to the control room, it is subjected to noise as well as atmospheric disturbances. So by using this instrumentation amplifier, we are just amplifying the low level signals and we are rejecting the noise which is present on that signals, and the input levels are very low levels. Those are millivolts as well as nano volts range. Okay, next, here I am going to explain the definition of instrumentation amplifier. Instrumentation amplifier is nothing but a difference amplifier. Already we studied about the difference amplifier. The output voltage of the difference amplifier is directly proportional to the difference of input voltages. Similarly, the instrumentation amplifier also, the output voltage is directly proportional to the difference between the input voltages. So what I am representing is the output voltage V0 is directly proportional to V1 minus V2. So V0 is equal to A into Vd, where Vd is nothing but the difference of input voltages, which is nothing but V1 minus V2. Next, finally, the gain of the instrumentation amplifier A will be equal to V0 divided by Vd. Instrumentation amplifier is also called as data amplifier. Okay, and the output of the transducer is a low level signals. So it is not possible to drive the next stages of the system. So what we have to do is, before applying the output of the transducer to the next levels of the system, we have to amplify the output of the transducer with the help of instrumentation amplifier. Why we are going to use the instrumentation amplifier to amplify the transducer output is, generally the output of the transducer is very low level. So to amplify the low level voltage sources, we have to use the instrumentation amplifier. Okay, instrumentation amplifier is also called as data amplifier also. Now second one, we completed the introduction. Next, we are moving on to the good requirements of the instrumentation amplifier. Mainly, we are having 9 good requirements for the instrumentation amplifier. What are they? First one is stable and finite gain. Okay, first one is stable and finite gain, and coming to the second one is variable gain. Okay, variable gain, and the third one is input impedance, which is nothing but high input impedance, and fourth one is low output admittance. Okay, low output admittance. Fifth one is low power consumption. Okay, low power consumption, and sixth one is high sleeve rate, and the seventh one is low thermal drifts. Okay, low thermal drifts, and eighth one is high CMRR. Last but not the least, ninth one is it requires 2 input signals to amplify the input voltages. Okay, so it requires 2 input signals. Okay, These are the main 9 good requirements of the instrumentation amplifier. So now we are going to discuss individually about all the good requirements of instrumentation amplifier. Coming to the first one, stable and finite gain. So we are receiving the output of the transducer from the longer distances to the control room. So we require stable as well as finite gain. Why? Because the instrumentation amplifier is amplifying the low level signals. So the output of the transducer is low level signals. So to amplify that low level signals, we require stable as well as finite gain. And for this instrumentation amplifier, we are using the closed loop op amps. Automatically, the closed loop op amps will consist of finite gain when compared with the open loop op amps. And the range of that finite gain is from 1 to 1000. And coming to the variable gain, not only the stable and finite gain, the instrumentation amplifier also requires the variable gain, which is also required. Precise range of variable gain also will be required to amplify the low level input signals. That will be done by using the potentiometer as well as digitally we are using the switches like JFET switches are using with the help of FETs. And next, high input impedance. The instrumentation amplifier is amplifying the low level signals. To avoid the loading on the input stage, we are using the high input impedance for the instrumentation amplifier. And coming to the low output admittance, to avoid loading on the immediate output stage, okay, we are going to be used the low output admittance. And coming to the high input impedance, there we are having two types. One is differential input impedance as well as common mode impedance. And the differential input impedance will be represented as ZID and common mode input impedance as represented as ZIC. Okay, and the differential mode input impedance is applied between the two input terminals, and the common mode input impedance is applied one of the input terminal and ground. And next, coming to the low power consumption, generally the instrumentation amplifiers are utilizes very less amount of the power. And sixth one is high slew rate. What is the use of this high slew rate in case of instrumentation amplifier? So to avoid the undistorted output, we require high slew rate. Slew rate is nothing but the rate of change of output voltage, maximum rate of change of output voltage with respect to time. If the output is varying with respect to time, then we will get the undistorted output. For that, we require the high slew rate. And next one is low thermal drifts. So instrumentation amplifier parameters does not vary with the help of temperature as well as time. Okay, so low thermal drifts are required. Okay, next, high CMRR. This is the main important requirement of the instrumentation amplifier. Why? Because the output of the transducer is coming from the longer distances to the control room. Okay, now while it is transferring from the longer distances to control rooms, we are going to be used the transmission lines as well as connecting wires also. So while it is traveling from the longer distances to the transmission lines, what happened is the input signal is subjected to noise as well as atmospheric disturbances. So high CMRR is avoid that noise, common mode noise present in the input signals. So the instrumentation amplifier requires high CMRR than the differential amplifier. And last but not the least is it requires two input signals. Why it requires two input signals is to amplify the difference between the two input voltages. That's why we require the two input signals, and these are all the main requirements of the instrumentation amplifier. Okay, now so some of these requirements are also used for the differential amplifier. Then why you are not using the differential amplifier to amplify the low level signal is why? Because the differential amplifier is not having high input impedance than the instrumentation amplifier. When compared with the differential amplifier, the instrumentation amplifier is having very high input impedance, as well as when compared with the differential amplifier, the instrumentation amplifier is having low output admittance. And similarly, when compared with the differential amplifier, the high CMRR value of the instrumentation amplifier is very high when compared with the differential amplifier. Because of all these things, we may not use the single-ended output differential amplifier or balanced output. There we doesn't require any balanced output. Why? Because the instrumentation amplifier is having only one output. So because of all these requirements, we are going to be used the instrumentation amplifier to amplify the low level signals. Till now, we discussed about the introduction as well as good requirements of the instrumentation amplifier. Now, we are going to discuss about analysis of instrumentation amplifier. Very important thing, analysis. Okay, so with the help of 3 op-amps, we are going to analyze this instrumentation amplifier. What are those 3 op-amps? Those 3 op-amps will be divided into 2 things. Input stage, we are having 2 non-inverting inputs, and at the output stage, we have the subtractor. So here I am considering non-inverting op-amps. Okay, I am considering 2 non-inverting op-amps. Here it is plus and here it is minus, plus, and here I am going to take it as minus, and the input is applied at the non-inverting terminal V1, and here also I am going to take it as plus and here it is minus, and again here I am applying the input as V2. Okay, and then next I am applying feedback resistance RF1. Okay, and for the second one I am applying the feedback resistance as RF2. Here I am connecting the variable resistance RG. Okay, and here we are getting the output voltage as V01, and here we are getting the output voltage as V02. Okay, these 2 output voltages are applied to the difference amplifier. Okay, or subtractor. Okay, here I am going to take it as R1, and here it is R2, and this one will be taken as R1. Okay, and here I am going to take it as R2. So this will be connected to here plus and then minus, and here I am getting the output voltage as V0. Now this is the circuit diagram. Okay, now this is the circuit diagram we required for the analysis of instrumentation amplifier. With this circuit diagram, I am going to explain the analysis of instrumentation amplifier. Here we required 2 non-inverting op-amps. What are they? A1 is non-inverting op-amp and A2 is also non-inverting op-amp, and A3 op-amp is nothing but the subtractor or difference. Okay, now what is the definition of non-inverting op-amp? Tell me, anyone? Coming to here, the definition of non-inverting op-amp is we are apply the input at the non-inverting terminal. If you observe this two op-amps, these two op-amps A1 and A2, here I applied the input at non-inverting terminals, which is nothing but the positive terminal. Okay, and the feedback resistance are RF1 and RF2, and those feedback resistances are connected with the help of potentiometer RG. And coming to the A3 is nothing but the subtractor. The two outputs of the non-inverting op-amps are applied as an input of the subtractor, and finally the output voltage of this instrumentation amplifier we will get as V0 is equal to R2 by R1 into V02 minus V01. Okay, this is the output voltage of the instrumentation amplifier. What I told you is just now, the total circuit will be divided into two parts. One is input stage and the other one is output stage. At the input stage, we are having two non-inverting op-amps, and at the output stage we have a subtractor. Okay, so for calculation of the output voltage V0, what I am going to consider is I am considering this circuit initially, input stage circuit initially, to calculate V01 value and V02 value. Once I will get the inputs for the subtractor, then just substitute by this formula, we will get the output voltage. So coming to this case, here I am considering the input stage. Input stage is nothing but non-inverting op-amps. Here it is A1, and here I am applying V1, and here I am considering it as A2, and here it is plus and minus, and here it is V2, and here I am connecting a feedback resistance RF1, and here it is RG, variable resistance, and here we are connecting another feedback resistance RF2. Okay, and here we are calculating V02, and here we are calculating V01. Okay, now so first I am going to calculate output voltages of two non-inverting op-amps. I want to represent output voltage in terms of V1, V2, RF1, RF2 and RG. So first what I am assuming is the input current drawn at the input terminals of an op-amp is 0. So what happened? The current passing through the op-amp is same. Okay, now so the current passing through the op-amp is same. So here I am going to consider it as the potential is A, and here it has potential is B, and here I am considering the potential is C, and here I am considering the potential is D, and here I am taking the potential as G, and here it is taken as H. Now see this one. If you observe this A1 non-inverting op-amp, we are applying the input at node A. So due to the virtual ground concept, what about the potential at B? Same voltage what we have at the node A. So VA is equal to V1. So obviously because of the virtual ground concept, VB is equal to V1. And if you observe this, B and G are connected together. So the potential at B will be equal to the potential at G. So what happened? VB is equal to VG is equal to V1. Okay. Next, coming to the second non-inverting op-amp. In this case, the potential at at D is equal to V2. Due to the virtual ground concept, the potential at C is also equal to V2. So D is equal to V2. So obviously the potential at C is also equal to V2. And if you observe the circuit, C and H are connected together. So what happened? The potential at H is also equal to V2. So VH is also equal to V2. So VD is equal to V2, VC is equal to V2, and VH is also equal to V2. Now the total current passing through the op amp is, here I am calculating I. I is equal to what? V01 using Ohm's law. I is equal to V01 minus V02 divided by RF1 plus RG plus RF2. Why I am taking it as a series connection is the total current passing through the op amp is same. So RF1 plus RF2 plus RG. Okay, now if I am considering RF1 is equal to RF2, then what we will get? I1 is equal to V01 minus V02 divided by 2 into RF plus RG. Okay, now I am going to calculate the current in between the nodes G and H. So what happened for I? So I is equal to VG minus VH divided by RG. So what is VG and VH? VG is equal to V1 and VH is equal to V2 divided by RG. So take it as equation number 2 and take it as equation number 1. Both are currents and both will be equal. So 1 is equal to 2. Then 1 equal to 2. What we will get is V01 minus V02 divided by 2 into RF plus RG will be equal to V1 minus V2 divided by RG. So what I am going to write is, we require V02 minus V01 divided by 2 into RF plus RG. Take minus as common this side and this side. So we will get V2 minus V1 divided by RG. So V02 minus V01 is equal to, from this what we can write, V02 minus V01 is equal to 2 into RF plus RG divided by RG into V2 minus V1. Now if you coming to the output voltage of the instrumentation amplifier, V0 is equal to R2 by R1 into V02 minus V01. So you substitute this value in this equation, finally you will get V0 is equal to R2 divided by R1 into 1 plus 2 into RF by RG into V2 minus V1, which is nothing but the output voltage of instrumentation amplifier. This is totally analysis of the instrumentation amplifier. Now what I am going to explain is advantages of instrumentation amplifier. The input impedance of the instrumentation amplifier is very high. Just now only I told you the differential amplifier is having high input impedance, but here we are having non-inverting op amp. When compared with the other op amps, the non-inverting op amp is having high input impedance. Here we are using the combination of non-inverting op amps. Though the input stage will consist of high input impedance and the gain of the op amp is depends upon the external resistances. So while easily adjusting the resistances RG, we can get the stable and finite gain, and the output impedance of the instrumentation amplifier is low. Here we are using the subtractor at the output stage. The subtractor in output impedance is very low and CMRR is very high. The low level signals will be amplifying, so we have to reject the noise present on that low level signals. That means we will be eliminate and we will just amplify the input signals. And the instrumentation amplifier is utilized very less amount of the power. So all these are the advantages of instrumentation amplifier. So in today's class I discussed totally about the instrumentation amplifier. Power consumption of the instrumentation amplifier is also very low. So all these are the advantages. Now introduction is completed, good requirements is completed, analysis part is also completed. Last but not the least, advantages is also completed. That's it for the instrumentation amplifier.